Long before telescopes or atomic clocks, the earliest humans looked up. They watched the stars shift and the sun travel across the sky to track the changing seasons, learning that planting seeds at the correct moment meant the difference between starvation and survival. This diagram illustrates the moon's rhythm, which provided the first reliable clock. The moon waxes and wanes through a complete phase cycle every 29.5 days. 12 of these lunar cycles stack neatly together to create a year that spans roughly 354 days. But here we find a mechanical mismatch in our orbital system. Earth takes slightly over 365 days to complete its journey around the sun. When you lay the lunar year next to the solar year, the moon finishes its 12 cycles 11 days before the Earth finishes its orbit. Every ancient civilization that relied on the moon to measure time had to confront this 11-day math problem to keep their societies functioning. This chart shows how an 11-day deficit compounds over time. By the second year, the calendar is off by 22 days. By the third year, the gap swells to a massive 33 days, an entire month of missing time. Without a mathematical correction, the months on a strictly lunar calendar detach from the physical seasons. They begin to slide backward through the solar year. This timeline illustrates the resulting seasonal drift. If you schedule an autumn harvest festival purely by the moon cycles, within a decade or two, that exact same lunar date will land squarely in the middle of the sweltering summer heat. For communities relying on agriculture, this drift is disastrous. Celebrating a harvest before the crops have even grown means the calendar has lost its physical connection to the Earth's natural cycles. To solve this, early astronomers in India developed the lunisolar calendar. This system uses the phases of the moon to measure the months, but it firmly tethers those months to the solar year. This model shows how they tracked the 11-day drift until it accumulated to a full month, which happens every 2 to 3 years. Then they simply inserted an intercalary month called Adhika Masa into the calendar. This extra month absorbs the deficit and snaps the lunar dates right back into their correct seasonal places. The Gregorian calendar, which most of the world uses today for administration, handles the math differently. Instead of following the moon, it locks directly on the sun's 365-day cycle. This split view contrasts the two approaches. Because the Earth actually takes 365.25 days to orbit the sun, the Gregorian system adjusts by adding a single day to February every 4 years, rather than waiting 3 years to add a whole lunar month. That quarter-day estimate isn't perfectly precise either. To prevent the Gregorian calendar from slowly drifting, century years like 1700 or 1900 skip the leap day, unless they are cleanly divisible by 400. Whether adding an entire month or a single day, these rules serve the exact same purpose, keeping human schedules tethered to the unbending physics of our solar system. By the 1950s, India had over 30 different regional calendars in use, creating massive administrative confusion. In 1952, the government tasked the Calendar Reform Committee, led by astrophysicist Dr. Meghnad Saha, with building a unified system. The resulting Saka calendar, or Indian National Calendar, is a strictly solar calendar. It consists of 365 days in a standard year, providing a consistent framework for government broadcasts and official communications. But it retains its cultural identity. The months keep their traditional names, like Chaitra, Vaisakha, and Jyeshta, grounding the administrative calendar and local history. This diagram illustrates the alignment. The first day of the year, Chaitra 1, is hard-coded to the day after the vernal equinox, the exact moment the sun crosses the celestial equator. On the Gregorian calendar, this reliably lands on March 22nd. This hybrid structure creates a national standard that operates on modern astronomical precision while maintaining the vocabulary of ancient Indian timekeeping. This dual system explains a quirk you might notice on your wall calendar: why some cultural festivals have fixed dates while others seem to wander. Festivals like Makar Sankranti are strictly solar. They mark specific astronomical events, in this case the sun's transition into the constellation Capricorn during the winter solstice period. Because the Gregorian calendar is also solar, Makar Sankranti remains highly stable, arriving on January 14th or 15th every single year. Diwali, however, is calculated using the lunar cycle. The Festival of Lights occurs specifically on Amavasya, the new moon, of the lunar month of Kartika. Holi relies on a different phase entirely, celebrated when the moon is perfectly full during the month of Falguna. This calendar grid shows the result of that mismatch. Because the 354-day lunar year is shorter than the 365-day solar year, these lunar-based festivals fall 11 days earlier on the Gregorian calendar each passing year, making them appear to bounce around. They bounce backward until the gap grows large enough to trigger the Adhika Masa, the extra lunar month. That mathematical safety net catches the festivals and pushes them forward, ensuring they always happen in the correct season. A calendar is a set of rules, and those rules tell us what a society values. The Gregorian calendar values extreme solar consistency, prioritizing seamless global trade, civic administration, and rigid seasons. Luni-solar calendars prioritize the visible, nightly rhythm of the moon's phases, while continually doing the complex math required to respect the sun's agricultural laws. Tracking time is one of humanity's oldest scientific achievements. Our ancestors looked at the sprawling, chaotic movements of the sky and found a way to translate them into the order of the day. Decoding our calendars reveals the mechanics of the stars and the mathematical ingenuity humans use to bridge the gap between heaven and earth.